Welcome to your calculus course preparation session. Today, we are diving deep into Introduction to Calculus, mastering limits and derivatives step by step, and by the end of this lesson, you are going to walk away with complete clarity on this topic. So let's get started. Calculus is essentially the mathematical study of continuous change. Unlike algebra, which deals with static formulas, calculus allows us to understand dynamic systems, like a rocket launching or a stock market fluctuating. There are two main branches you need to know. Differential calculus, which we are focusing on today, deals with rates of change and slopes of curves. Integral calculus focuses on accumulation, like areas under curves. But before we can master either of those, we must understand the concept of a limit. Limits form the absolute foundation of all calculus. They tell us what value a function approaches as the input gets closer to a specific point. Let's break this down and write out exactly what a limit is. The formal concept is that a limit is the specific value a function approaches as the input, usually called x, approaches some target value. It is all about the journey, not necessarily the destination. We write this using a specific notation, lim, as x approaches a of f of x equals L. When you see this on your exam, you read it as the limit of f of x as x approaches a is L. Now, here is your anchor fact for this topic, the key rule you must remember: the function does not actually have to reach the value L exactly at point A. It just has to get infinitely close to it from both sides. Sometimes, there is a literal hole in the graph at that exact point, but the limit still exists because the path clearly points to that specific value. Now, let's actually solve a limit problem together. Here is our question: evaluate the limit of 3x squared minus 4x plus 1 as x approaches 2. The very first thing you should always try when evaluating a limit is direct substitution. So, we simply substitute x equals to directly into our expression. Next, we evaluate the exponent. 2 squared is 4, so our expression becomes 3 times 4 minus 4 times 2 plus 1. Now we just multiply our terms out. 3 times 4 gives us 12. And 4 times 2 gives us 8. So we are left with 12 minus 8 plus 1. Finally, we simplify this basic arithmetic to find our final limit. 12 minus 8 is 4, plus 1 equals 5. So, as x gets infinitely close to 2, the value of this entire function gets infinitely close to 5. Direct substitution worked perfectly here. So, how do limits help us find derivatives? Let's look at the conceptual flow of how a derivative is born. We start with a secant line. A secant line cuts through a curve at two distinct points. If you calculate the slope of this line, you get the average rate of change over that specific interval. Think of this as calculating your average speed during a road trip. But what if we want your exact speed at a specific millisecond? We shrink the distance between those 2 points. We apply a limit, bringing the second point infinitely close to the first point. The distance between them approaches 0. When that distance becomes infinitesimally small, the secant line transforms into a tangent line. The tangent line touches the curve at just one single point. The slope of this tangent line is the derivative. It represents the instantaneous rate of change. This is the core magic of differential calculus. Finding the derivative using limits every single time takes way too long. Luckily, we have shortcuts. Let's write down the most important one. The purpose of the power rule is to give us a fast, reliable shortcut to find the derivative of any function where a variable is raised to a constant power. You will use this constantly on your exams. Here is the formal rule: if your function, f of x, equals x raised to the power of n, then the derivative, denoted as f prime of x, equals n times x raised to the power of n minus 1. Let's put that into plain English so it sticks in your brain. To apply the power rule, you simply take the original exponent, bring it down to the front to multiply it by the coefficient, and then you subtract exactly 1 from that original exponent. Bring it down, subtract 1. That is the entire mantra you need. Let's put that mantra to the test and solve a derivative problem step by step. Our function is 4x cubed minus 5x squared plus 7. We take the derivative term by term. For the first term, 4x cubed, we bring the 3 down. 3 times 4 is 12, and we subtract 1 from the exponent, leaving us with 12x squared. Now for the second term, negative 5x squared. Bring the 2 down. 2 times negative 5 is negative 10. Subtract 1 from the exponent, 2 minus 1 is 1, so we just write negative 10x. What about the plus 7? Well, the derivative of any standalone constant number is always 0. Why? Because a constant doesn't change, so its rate of change is 0. Finally, we combine our terms to get the final derivative. F prime of x equals 12x squared minus 10x. You just found the instantaneous slope. To make sure you truly understand, let's compare these two foundational concepts side by side. First, look at the core question they answer. A limit asks, where is the function going as we approach a specific point? A derivative asks, how fast is the function changing at that exact point? Geometrically, a limit simply represents a specific y-value on a graph that the curve is aiming for. A derivative, however, represents the steepness or the slope of the tangent line touching the curve. You can easily spot them by their notation. Limits use the lim abbreviation with an arrow showing the approach. Derivatives use the prime notation, like f prime of x, or the Leibniz notation, dy over dx. Finally, consider their dependency. The limit is an independent, foundational concept. The derivative, on the other hand, absolutely requires limits to even exist. The derivative is literally defined as a specific type of limit. Let's pause for a quick knowledge check to make sure you have mastered the power rule. Here is your question. What is the derivative of the function f of x equals to x to the power of 4? Option A says 8x cubed. Option B says 4x cubed. Option C says 8x to the power of 4. And option D says to x cubed. Take a brief moment, remember the mantra we discussed, bring it down, subtract 1, and pick your answer. The correct answer is A, 8x cubed. Why? Because you bring the exponent 4 down and multiply it by the coefficient 2, which gives you 8. Then, you subtract exactly 1 from the original exponent of 4, which leaves you with an exponent of 3. If you chose A, you are doing fantastic and are well on your way to mastering basic differentiation. You might be wondering, why does any of this matter outside of a math classroom? Calculus is the language of the universe. In physics, if you have a function that describes the position of a moving object, the first derivative gives you its velocity, how fast it is moving. Take the derivative again, and you get its acceleration. This is how engineers calculate rocket trajectories. In economics, derivatives are used to find marginal cost and marginal revenue. If a company wants to maximize its profits or minimize its costs, they use calculus to find the exact peak or valley of their profit graphs. Even in biology, calculus is essential. Epidemiologists use derivatives to model how quickly a virus is spreading through a population, or how fast a bacterial culture is growing in a petri dish. Whenever you need to predict a rate of change in the real world, calculus is the tool you will reach for. Let's do a rapid-fire recap to lock these concepts into your long-term memory before we finish. First, the value a function approaches as x approaches a is called a limit. Next, the slope of the tangent line at a specific, instantaneous point is known as the derivative. Finally, the shortcut to find the derivative of x to the power of n is called the power rule. Excellent work today. And that wraps up everything you need to know about Introduction to Calculus, mastering limits and derivatives step by step for your calculus course journey. You now have a solid foundation in how continuous change is measured mathematically. In our next class, we will be moving on to the chain rule and more advanced differentiation techniques, so make sure you stay tuned. For more practice problems and interactive study tools, visit Examiverse AI Studio platform to learn more.